This video deals with one especially interesting consequence of the fact that the force on a charged particle in a magnetic field is always perpendicular to the direction of the particle's initial velocity. And that is that a charged particle entering a magnetic field can be moved in a circular path, or at least part of a circular path. So for example, here we see a magnetic field pointed out of the screen. That's what all the dots mean. And we can see the charged particle moving up the screen. So go ahead and set up your right hand so that your fingers are pointed out of the screen and your thumb is pointed up. You'll see that there is a force therefore to the right on the screen, but as soon as the particle enters, its velocity vector changes direction. So you would have to continuously move your right hand so that your thumb is pointed in a different direction. That's what that black vector means the entire time. The green vector on here the entire time should represent the direction of your right hand's palm if you're doing the right hand rule to determine the direction of the force. So this is definitely not projectile motion like we saw with charged particles in electric fields. It is possible, under certain circumstances, to get a charged particle to move in a complete circular path, continuously. Based on the strength of the magnetic field and the speed at which it's moving, you could relate the equation of circular motion, the acceleration in circular motion being v squared over r. You could relate that to the force that we just learned, qvb sine theta. That is to say, if a magnetic field is causing a charged particle to move in circular motion, then the magnetic field is providing a centripetal force. That takes us back to first semester physics, where we learned that the centripetal force is equal to the mass of the object times the centripetal acceleration, v squared over r, where v is the velocity, or rather the magnitude of velocity of the object, and r is the radius of the circle. Well, we know that the force exerted by the magnetic field is the force that's causing mv squared over r. And the force that the magnetic field is exerting is qvb sine theta, where theta is the angle between the direction of the magnetic field and the direction of the velocity of the particle. Well, if the magnetic field is pointed, for example, into the screen, as here, then it is perpendicular to the direction of the velocity of the particle at every point on this page. So sine theta would be sine of 90 degrees, which is 1. So the sine theta part actually just becomes 1, and we get that qvb equals mv squared over r. The v on both sides of that equation is the same, so I can divide out the v on the left with part of the v squared on the right. That equation right there, qb sine theta equals mv over r, is the equation that governs the motion of a charged particle moving in a circular path due to a magnetic field exerting a force on it. This requires that the magnetic field be constant the entire time. Notice that this is, again, a particle that is accelerating, but not one that is speeding up or slowing down. So again, you have to take yourself back to first semester physics to remember that that means the object is changing direction the entire time. As usual, I do not recommend that you take any part of this series of equations and memorize it or write it on an equation sheet. My recommendation is that you realize that the circular motion is governed by the physics of circular motion. But if it's caused by a magnetic field exerting a force on a charged particle, then it is also governed by the equation we know for that. So we could set those two equations equal to each other and rearrange it to solve for whatever a particular question happens to ask. An excellent example of how this is useful is that a mass spectrometer can use a constant magnetic field to exert a centripetal force on particles, and the radius of motion of the particle would depend on the mass of the particle. The more massive it is, the larger the radius, because it's more difficult to make that particle accelerate, change motion. In Physics 150L, under normal circumstances, we do have a lab where we bend a ray of electrons. That's what that beam is right there. That's a ray of electrons, and we bend it around into a circular shape with a magnetic field that we control. So that beam of electrons is initially pointed straight up. If the beam of electrons is pointed straight to the top of the screen right here, what direction is the magnetic field that is causing it to bend in this circle? Maybe I'll give the answer in class, or maybe I'll ask you to. That's it for this video. See you in the next one.